Okay, hello class. This lesson here we're going to move on from the gas laws to the ideal gas law. And the ideal gas was introduced before in the first section, just mentioned some of the properties of a gas that behaves ideally. For chemists to be able to model gases, sometimes approximations need to be made. And the ideal gas law would be an example of that. You'll see the characteristics of an ideal gas will have you questioning how effective that formula would be at modeling a true gas. However, you will have an opportunity in this section here to look at the measurement of the molar mass of a gas, which is a very simple method, and we can work on this as a class to determine how heavy butane is as a molecule in grams per mole. Today we're going to look at three little video clips here just to summarize the three gas laws that we've seen previously that contributed to the combined gas law. So let's have a look at these just as a review.
If the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
Okay, so in this first one, we were looking at pressure volume. This is Boyle's law. We have constant temperature. The gas is not being heated or cooled. We have constant amount of gas. Gas is not entering or leaving the system. As we decrease the volume of the gas, the pressure increases. More collisions with the container walls increases the pressure. Let's have a look at the next one.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore, so does gas pressure.
So look at those molecules move. Now this one here is the effect of temperature and pressure with constant volume. So this would be Gay-Lussac's law. We examine this. There's two factors that contribute to the increase in pressure, the increased number of collisions and the energy of each collision. Let's move on to the third law, which goes back and looks at the temperature volume law. Now for the temperature volume law, we don't have a little video clip to show for this one, but what I can do is go back and look at Charles' law has volume and temperature related directly, and because of that we saw that the ratio of volume to temperature was approximately constant in experimental trials, meaning that volume as a function of temperature would be a straight line, and because of the constancy of the volume temperature relationship we get the formula which we now know as Charles' law. So this is constant pressure, constant amount of gas. This law can be used to explain why a gas expands when it's heated, as we have a starting temperature here, we'll call this T1, and move to a new temperature here, T2. We have a starting volume, V1, and a new volume, V2. And if we were to say that temperature approximately triples, in other words T2 is equal to 3T1, we would expect that as a result volume would also triple. And this formula here would predict that simply because the fact that if we rearrange this for volume 2, we get V1 multiplied by T2 over T1. Now part of this formula here has a ratio for T2 over T1. Going back to the idea that if the temperature tripled, what that means is the ratio of the second temperature to the first is 3. So we can use that fact here, and going back to the formula we see that, well, this formula would predict that when we triple the temperature, we would also triple the volume. V2 equals 3V1. And this is, of course, what we arrived at when we inferred that the tripling of the temperature would triple the volume. Okay, so this is a direct relationship here. Now the third, actually the fourth relationship, which we haven't looked at yet, but is very easy to demonstrate, is that as the amount of gas increases in a system, so too will the volume of gas. And a simple demonstration of that would be inflating a balloon. You inflate a balloon by blowing more air into it. Okay, the pressure of the balloon doesn't increase in that situation because as it expands, it's always balancing with atmospheric pressure. So the shape of the balloon will be dictated by the pressure around the gas outside of the balloon, and it will occupy a certain volume. So under constant pressure, the volume will increase as the amount of gas increases. This can also be illustrated through a simple simulation. Let's have a look at that.
If the number of gas molecules in a container is doubled, with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
All right, well that actually was a demonstration to show that the pressure will increase as the amount of gas increases in a fixed volume. So that shows both. What we want to focus on in the ideal gas law is the relationship between volume and all of the other factors that can affect that property of a gas. So as we go through here, we'll be looking at proportionalities and trying to combine them all into a single formula which relates the four possible properties of a gas: the pressure, the volume, the amount, and the temperature. Okay, we're going to move forward here and look at the relationships between volume and these three other variables. The first point that you want to fill in your handout here is that based on these simulations we've seen and the discussions we've had, volume varies with three properties of a gas. It's pressure, which is an inverse relationship, the temperature, which is a direct relationship, and the molar amount of gas, which is also a direct relationship. The symbol here, which looks a little bit like a fish, means varies with. Okay, or also could be described as proportional to. Okay, so if something is proportional to, that means that it varies by a factor. So if it's inversely proportional to pressure, then we would find that if the pressure doubled, then volume would vary with a factor of a half. If the pressure was cut in half, then it would vary with a factor of 2. Okay, so we can kind of just apply the change to the pressure as a factor, and we can get the change in volume as a factor. So that's how that works. If we look at the direct variations, those are a little bit more intuitive. If volume varies directly with temperature and molar amount of gas, then if we increase the molar amount of gas by 1.5 times, the volume would increase by that same factor. If we were to warm something to, say, 10% above its current temperature, we would find the volume would increase by that same 10% amount. So these three proportionalities separately allow us to solve for volume in terms of the other three. If we combine them, we would find that as a single proportion, we could have all three properties of the gas potentially changing: pressure, temperature, and molar amount of gas, and that would give us a single proportional relationship. The simple matter of just tacking them all together as a product. Okay, and that's consistent with what proportional is. So if temperature was to double and molar amount of gas was to triple and the pressure was to double, we could use all of those changes to come up with the total change to our volume. Now, that's not an equation exactly, but it's a proportional relationship. As an equation, it looks a little bit the same, except now we want to be able to solve for the volume, and we can use a proportionality constant, which we've seen in the past. And we can also see here that the proportionality constant for the ideal gas law is substituted with this symbol capital R, which is a constant for a gas, and chemists have determined this constant to be 8.31, and it has units that, when placed into the formula, will produce liter as a unit from all of the other units involved. So it has to have itself not only a number but units attached to it, and the units for this ideal gas constant are kilopascal liter per Kelvin mole. Elsewhere in some textbooks you may see this look a little different. You may see this look like kilopascal liter Kelvin and mole, both with an exponent of -1. That would be a common product, which would use a reciprocal of Kelvin and reciprocal of mole as a unit. But for our purposes, we can just know that whenever we use the ideal gas law, we're going to produce the units of liters for volume. So volume would be in liters. We would have pressure, again, in kilopascals, number of moles, as before, in moles, and finally temperature would be in kelvins. So the ideal gas law is usually written where pressure and volume are on the left side, and N, R, and T are on the right side. Of course, if we want to relate them all to volume, then it would be a product of N times R times T divided by P. Okay, so that is the ideal gas law. Properties of an ideal gas, we come back to this again, are as follows. You can write these down. The forces between molecules are assumed to be zero. In other words, they don't interact beyond colliding. They don't cause each other to be attracted or repelled. All motion of particles is assumed to be straight line motion. Okay, we assume that as an ideal gas, they behave perfectly with regards to pressure, temperature, and volume temperature relationships, which means that the VT relationship is perfectly direct, and the pressure temperature is also perfectly direct. So linear straight lines for the graphs. The other property, which is a little bit of a stretch, but this is sort of a consequence of cooling a gas. At some point, the gas isn't a gas anymore, it becomes a liquid. And we have to keep that in mind, that there is such a thing as a melting point and a boiling point. And at the boiling point, it's a transition between the liquid phase and the gas phase. So you can't cool a gas continually and expect it to remain as a gas, but an ideal gas is assumed to have that property. Okay, for the most part, when the ideal gas formula is used, we're using it under gas phase conditions. So those assumptions really hold up well for the conditions that we study gases. Let's see, for applying the ideal gas law, we have your handout here now, which should have been completed. Some questions here that we're going to work through. For the rest of this lesson, I think what I'll do is I'll go through questions involving the ideal gas law from the student worksheet. In this instructional master, you just see the proportionality that we've come up with, combining these into the single formula PV equals nRT. And the sample problem here shows the application here. If you have 880 milliliters of gas at a 90 kilopascal pressure and a temperature of 30 degrees Celsius, what would the mass of the gas be? So in this case, we need to first of all determine the number of moles, N. We have the ideal gas constant at 8.31, and temperature has to be in Kelvin. So by substituting all of our values in, rearranging the formula to get moles equals pressure volume divided by constant times temperature, we can come up with the molar amount, and then we use the molar mass of neon, which is 20.18 grams per mole. So this is the calculation of mass equals moles times molar mass. So we get 0.63 grams. So that's a fairly simple formula to work with, but what's nice about it is it allows us to make a connection between moles, molar mass, and grams for the mass of the gas to the other properties which are typically measured for a sample. Okay, looking at the student worksheet 9.4a, you have the solutions on the PDF with this video as an attachment. So what I'll do is I'm just going to go through these questions here and just outline the formula that would be used, just to make sure that you see how to solve for different properties for a gas from PV equals nRT. And then you have your answers which you can check, and in the assigned work I've indicated that for extra practice here, when you finish working on some group work questions and some independent questions from the textbook, for extra practice you can do more on page 448, or you can complete the student worksheet. So if you have done the student worksheet after having practiced a little bit, then you can skip out on these questions here from the section questions of 9.4. So we will be doing as a class investigation on determining the molar mass of a gas. This here is the setup. So you will want to read through that and be prepared to complete that. In class, you will have to do the prediction to determine the molar mass of butane, which is a hydrocarbon, and it has C4H10 as its chemical formula. Read the procedure as well for that. That'll be happening the next couple of days in class. So we've returned this to the student worksheet now. We're looking at what amount, in this case for the moles, is unknown, and we're going to find out from the formula that to solve for N would just be a matter of rearranging, and most of the rearrangements are pretty simple here. We'd take both sides and divide by R times T, and that would give us nRT over RT. So we'd get, therefore, N equals PV over RT. So that allows us to solve for moles. The only thing we have to do here is convert to Kelvin. And of course, to get Kelvin from Celsius, we were always adding 273. So 293 Kelvin, 600 cubic meters. Now here, what you'll have to do is you have to make a conversion, and the equivalence here is that there are 1,000 liters for every 1 cubic meter. So you'll need to know that equivalence as well. Now that's indicated over here. A cubic meter is the same as a kiloliter. Pressures in kilopascal, so that question should be straightforward once those conversions are made. Number 2 is calculating the mass of gas. Now, here I'll just point out that you could take your formula PV equals nRT, and you could actually replace N with mass over molar mass. And so what you have here is sort of a variation of the ideal gas law, which allows for us to solve for M. So I'll rewrite that as mass of the gas times the ideal gas constant times temperature all over the molar mass of the gas equals PV. So if I want to solve for the mass, I multiply both sides by the molar mass, and that would give me PVM equals little m RT, and then I can divide both sides by RT again, and I can get pressure, volume, molar mass divided by ideal gas constant and temperature equals little m. Here, pressure is in kilopascals, volume is in liters, temperature is in degrees Celsius. So again, the only thing we need to do here again is convert this to Kelvin. Okay. Number 3, we're going to look at calculating a volume. So here, we may want to start out with volume equals proportional to temperature in moles. So they should be in the numerator. Inversely proportional to pressure should be in the denominator. So that's a variation of the ideal gas constant, which would be more convenient to use here. Now, because we have mass given instead of moles, again, there we could replace that with mass times ideal gas constant times temperature divided by molar mass. And here we have in that we have mass over molar mass, which is the equivalent to moles. So we could figure out for nitrogen, remember nitrogen is diatomic, so we would want to recall that we have chemical formula of N2, so we'd have to determine the molar mass of nitrogen gas. Everything else should, again, as before, this needs to go to Kelvin, and our pressure is in the correct unit. So that one should involve just a couple of conversions. Moving on to number 4. Hydrogen gas is generated by the decomposition of water. So in this case, we have water, liquid. Under electrolysis, we can pass electrical current through the water and decompose it into hydrogen and oxygen. And here our chemical formula is just to kind of help us understand the type of reaction going on. This is a 2 and 2 and a 1 mole ratio. So we have 20 degrees Celsius and 100 kilopascals of pressure filling a 1.1 kiloliter weather balloon. Again here 1 kiloliter is equal to 10 to the 3 liters. Trying to determine the mass of hydrogen that is required. So here it would be again using the formula that we generated from question number 2. This would probably be the best way of just reusing something we've already isolated, so we can refer back to that and just recall that again hydrogen is diatomic, so your molar mass of hydrogen H2 needs to be determined, and your temperature needs to be converted again into Kelvin. Okay, and getting close to the last one here, we can look at number 5. There we go. Finishing up with number 5, calculate the volume of 16 grams of oxygen at 22 degrees Celsius, 97.5 kilopascals. Very similar to number 3. So again, we had solved for volume in terms of mass, molar mass, and temperature. So we can again recycle our formula from number 3 and then reapply it here. So you should get lots of practice with the ideal gas law. Pretty simple formula to use. Just make sure you have your units in the correct form and watch for little prefixes in your units such as kilo that might require just an adjustment by a simple factor. So again, going back to sign work here, review your note, make sure you have everything filled in, and looking into class to be working on these questions here, and I would encourage you to start reading the investigation 9.41 to prepare for that lab activity. Bye. Ample of gas.